Chapter 4, Problem 10. Before going into orbit, an astronaut has a mass of 55 kilograms. While in orbit, a measurement determines that a force of 100 newtons causes her to move with an acceleration of 1.90 meters per second squared. To regain her original weight, should she go on a diet or start eating more candy? Because it's a she, I figured I'd get a picture of a female astronaut. I looked up her name too. So her mass is originally 55 kilograms. Now she is on board the space station or the space shuttle, and while in orbit, a measurement determines as a force of 100 newtons causes an acceleration of 1.90 meters per second squared. So mass times that acceleration, force equals mass times acceleration. So it's going to be 100 divided by 1.90. Come up with 52.6 kilograms. So 52.6 kilograms. So that means while in orbit, she has lost 2.4 kilograms due to the typical body mass loss that astronauts experience when they're outside of gravity, because their bones don't have to support their body anymore, and so while they're still eating, they're still easy for them to lose some of their mass. So they're on an interesting diet. So it's important for them to actually keep track of their mass. Now the thing is, in orbit, how do they actually measure their mass? Back on Earth would be easy, just stand on a scale, but a scale is not going to work in orbit. So this one is being used, a body measurement device where they strap themselves in, and then this one is set in motion. It vibrates forth and back, and by how much it vibrates forth and back, that tells the device what kind of mass is being strapped in, and that's how they determine their mass. So this is chapter 5, and I'm starting out with what's called a one-step calculation number 1, so I call this OSC. And even though the chapter name is Newton's third law, as I had mentioned before, for Newton's first law, Newton's third law, there's really nothing to calculate on the law of inertia. There isn't. On the action-reaction principle, it's pretty much if there is a 40 Newton force on one object acted on by another object, then, well, there's a 40 Newton force on the other object, just in the opposite direction, so there isn't really much to calculate. So even in this chapter, they're doing some Newton 2 problems. Okay, so let's look at the first one. It says, calculate the resultant of the pair of velocities 100 kilometers north and 75 kilometers south. Calculate the resultant if both of the velocities are directed north. And I'm going to start with the, by the way, I don't need the calculator here. I'm going to start with the second part, which says that both of them are north. So this one here is pointed 100 kilometers per hour north, and this one is pointed 75 kilometers per hour north, and then I just add the 2, and it looks like this, and I think we already know that we come up with 175, but this is the way on how to do it properly. And so that's how to add them, and it's pretty much in order to add them by vectors go from the tail of the first vector to the tip of the last vector. So from here to here, align them tip to tail, and then go from the tail of the first vector to the tip of the last vector. And obviously I do come up with, when I add these here, come up with 175 kilometers per hour for the second part. Okay, the first part says, I'm gonna grab these two here and copy them. There we go. But this one now points in the opposite direction. And again, they're added in the same way. Put them tip to tail. And maybe I shift them just a little bit here so to align them nicely with the squares, hopefully. Yeah, I think that looks a little better. There we go. So tip to tail, just like I did over here. And now the resultant is going from the tail of the first to the tip of the last. And when you look at it, 100 kilometers per hour north, 75 kilometers per hour south, you would have to subtract them. You come up with 25, and that's what the arrow is showing here as well, 25 kilometers an hour. The next problem says, calculate the magnitude of the resultant of a pair of 100 kilometers per hour velocity vectors that are at right angles to each other. So each one of them is 100 kilometers, and in order to add these properly, I know in the book he uses the parallelogram rule. I like to do it this way: tip to tail, the two vectors, and then I go from the tip of the first to the from the tail of the first to the tip of the last vector. I hope I had mentioned it in the previous problem as well. And that's what I come up with. And now I can measure that. And let's see. So this here would be 100. I know it's not totally parallel, but close enough. That's a little better. I don't think I get it any better. I don't get it any better than that. So it's 100 right here, and now I'm trying to find that spot right there. I believe it was here. So 140. By doing this graphically, 140 kilometers per hour. And if I do it by algebra, by the way, I forgot to write down here that this is chapter 5, one-step calculation number 2. Okay, so if I do this according to the algebra, they're saying that if they are at right angles to each other, then the resultant vector r equals x squared plus y squared. Take the square root, so it's going to be 100 kilometers per hour squared plus 100 kilometers per hour squared, and then take the square root of that. And when I do that on the calculator, I come up with the square root of 100 squared plus 100 squared, parentheses, enter, 141. Well, that's what I measured as well, 140. There's a quick way, but it only works if it's a right angle and if the two vectors are of equal length. And that quick way is that I take 100 and I multiply it with the square root of 2. But as I said, that only works if the two vectors are of equal length and are at right angles to each other.